Hey, this is Horner, and this is section 10.8, which is power. Power is really just the rate at which energy is either transformed or transferred from one place to another, or one form to the other. And so power is equal to change in energy over the change in time. But remember, work is equal to the change in energy. So the equation you're typically used to for power is work divided by time. The unit is a joule per second, which we call a watt. And those two are the same. Typically, you'll see the word watt or you'll see the abbreviation W, and you don't always see joule per second. So they would prefer that you're using the SI unit, which is a watt. The other way of doing work, or talking about power here, using work, is to look at the output power of a force that transfers energy. So power here is work over time, but remember, work is force times distance, or change in position, divided by time. Change in position over change in time we know is velocity. So because that's velocity, we can say that it is force times velocity. And this is the rate of energy transfer due to a force acting on an object moving at a velocity of v. So you can think about how much power your car has at a certain speed, and then the change in the power, and all kinds of really cool stuff like that. For the next part, we're going to take a look at a quick check. This one says we have 4 students running up the stairs and the time shown. Which one has the largest power output? So remember, power is equal to work, which is change in energy, over the change in time. But for us, our energy here is potential. So we want to know what is our potential energy. We know our original is 0 because we're starting at the bottom. So we're just looking for final potential energy, which is mgy all over the change in time. So mass times gravity times y would be 8,000 here, divided by 10 would give us 800. Remember, our unit here is a watt. For the next one, we have 80 times 10 times 10 gives us 8,000 again, divided by 8 would give us 1,000 watts for the second person. For the third person, we'd have 6400 divided by 8, because it's 64 times 10 again, and that would give us 800 watts again. So A and C are equal. Right now B is winning. And finally, we have 80 times 10 times 20, and so that would be 16,000 divided by 25, and if you do that, you should end up with an answer of 640 watts. So our winner here has got to be letter B, and that should be the correct answer, which it is. So here we're using change in energy or change in potential divided by change in time. The next one's going to use change in kinetic energy in a change in time. So we have four toy cars. Actually, there are 5 of them. The masses of the cars, the final speeds, and the time to reach the speed are noted. They want to know which one has the greatest power. So for each one of these, we need to take 1/2 of the mass times the velocity squared and divide it by time, because power, remember, is change in energy. And if they start at 0, then we know that we can just use the final kinetic energy divided by the change in time. So we've got, we're going to go ahead and leave these in grams. Actually, let's go ahead and put them in kilograms. So 0.1, this would be 0.2, 0.3, 0.6, and 0.4. And we need to multiply 1/2 of each one of these times the mass times the speed squared. So we're going to square each one of these speeds. And then we're going to divide whatever the answer is for each one by the amount of time. So for the first one, we've got 0.5 times 0.1 times 9, which is 0.45 divided by 2, which gives us 0.225. So this table would be what our power is, and this would be in watts. And now we're going to do 0.5 times 0.2 times 4 divided by 2, and this gives us 0.2 watts. Next one is 0.5 times 0.3 times 4. Oops, we're going to do 0.5 times 0.3 times 4, and we're going to divide that one by 3, and this one is 0.2 watts. Do the next one, which would be 1/2 of 0.6, which is 0.3 times 1 would be 0.3 watts. Oops, 0.3, yeah, divided by 3 would give us 0.3, sorry, 0.3 divided by 3 would give us 0.1 watts. And then finally for the last one, we've got 1/2 of 0.4, which would be 0.2 times 4 divided by 4, and that would give us 0.2 watts again. So it looks like our biggest one is definitely letter A, and that is 0.225 watts. So that's example 10.21. For example, 10.18, we have power to pass a truck. We have a car, it has a mass of 1,500 kilograms. It's behind a truck traveling at 60 miles an hour, which is really 27 meters per second for us. To pass the truck, we have to go 34 meters per second in 6 seconds. They want to know what the power is. We're transforming chemical energy into kinetic energy, so we can find the change in kinetic and use the time interval to kind of help us figure out what's going on. So our original kinetic energy is about 5.47 times 10 to the 5th joules. So we used our speed and our mass, place those into the equation. We find out that our final kinetic energy is 8.67 times 10 to the 5th. And if we find the difference between the two, we get about 3.2 times 10 to the 5th joules. We want to take that change in energy then and divide it by the change in time. If we do that, we get about 53,000 watts. So it's about 71 horsepower. So that's in addition to the power needed to overcome all the drag and friction at 60. So that greater amount of power is going to be used in order to get us to go that fast and go buy our truck. The rest of this is just some general principles in summary. So we talked about the basic energy model. We looked at transferring energy. We looked at work. We looked at heat. We talked about conservation of energy, trying to solve problems with conservation of energy. Looked at kinetic and potential energies, and then said that mechanical energy is the sum of all those, or that's the total energy. And we skipped over thermal, but we did talk about work. And we did not talk about collisions, but then we ended up using power. And that is the end of this unit.